today about some interacting lattice fermions. Thank you very much.
Okay, so thank you. Thank you, Filippo, and thanks for the organizers for the invitation. So I'm very happy to be here at GGI as always. So this is the title of my talk, and so I will present some recent results that we had in Florence at Lens and Department of Physics and Astronomy. And okay, this is a brief outline of my talk that will be essentially divided into two parts, and then if time allows, I will tell you something more at the end. So I will spend some introductory words to the system that we are realizing and studying in the lab, and then I will focus on two different topics. So the first one is the observation of flavor-dependent localization of lattice fermions via controlled SUN symmetry breaking. Don't worry, I will explain everything to you step by step in the following. And then very recent results concerning the observation of Hall effect in strongly interacting fermions in the lab. So let's start with an introduction. So very general and also very brief, just to set the ground for the rest of the talk. So this is the kind of experimental system that we are interested in. So here you see a vacuum chamber, and inside this vacuum chamber you have this cloud of atoms that with the help of lasers we can cool down to temperatures on the order of a few billionths of a degree above absolute zero. So if you happen to come in our labs, and you're invited to do so. So if any of you is interested in coming to CESO and visiting the labs, so please tell me, and I will be happy of guiding you. So we have a lot of lasers. So lasers and optics, mirrors, spin splitters, fibers, and so on. And with the help of these classical hardware, we can build quantum systems inside this glass cell here. And there we try to play with some interesting quantum physics. So, so the idea is to try to achieve quantum control over a system of particles, of a many-body system. So this is what we are trying to do. And for this idea, so we want to engineer many-body systems where particles interact among themselves, and we want to study their behavior. One tool that we use quite a lot is given by optical lattices. So basically we can arrange these particles in a grid, in a lattice structure, with the help, again, of laser light, so in the form of standing waves of lasers, so counter-propagating laser beams that form this crystal of light. And so the atoms that are trapped at the antinodes of this standing wave, so basically behave for many respects, as the electrons inside the material, inside the solid, because they are quantum particles that experience a periodic potential, as in the case of what happens in real matter. So this is the analogy that is at the basis of a possibility of performing quantum simulations, and so one can really implement not just real materials that would be boring and useless, because I mean, it makes no sense to simulate something that already exists, but instead the idea is to try to provide some clean implementation of interesting models. And I will show you a couple of these during my presentation, and then also to achieve some kind of extreme state of matter. So play with the parameters, profiting of the tunability of the system, so to realize some state of matter that does not exist in ordinary matter. Okay, and in doing that, one of our specialties is the control of internal state of the atoms. So this will be important for the following. So each of the particles that we are dealing with, these are not elementary particles, so these are atoms. Atoms are quite rich objects, so with a lot of degrees of freedom inside, because they're made by many constituents. And so in particular, for the work that we'll present, we use ytterbium atoms that have some nice properties, in particular the fact that you have many stable states, internal states, either electronic or spin states, that we can manipulate quantum coherently. So we can drive transition between electronic states or control the spin state. And I'd like to point you to the fact that an atom is not a spin 1/2 particle, but can have a larger spin. So our atoms have a spin of 5/2. So this means in principle, 6 possible spin projection states that we can control in the experiment. And this is important for the first part of my presentation. So I will tell you 2 results concerning with actually with manipulation of a spin degree of freedom in these atoms that are, by the way, fermionic atoms. So these are fermions that interact among themselves with repulsive interactions, as we will see in a moment. And this is the system, the hardware that we use for performing our quantum simulation. So first topic. So first topic is this flavor-dependent localization via controlled SUN symmetry breaking that has been published at the end of last year in Nature Physics. And this is an experiment that we performed in collaboration with a theoretical group of Massimo Capone in SISTA Trieste. So let's start with something simple and well-known, that is the Hubbard model. So the Hubbard model is maybe one of the simplest condensed matter models that takes into account correlations between electrons in a lattice. So it's a tight-binding model that describes interacting electrons, spin 1/2 particles that can either tunnel from one lattice side to the next neighbor with this tunneling amplitude T, or they can interact one with the other. So spin up can interact with spin down repulsively if this interaction energy U is positive when the particles are sitting on the same side. So very simple model, tunneling and on-site interactions. And so the physics of this model has been studied quite a lot because also the connections with materials like cuprates, so ITC superconductors, in which it is believed that the superconductivity can be explained in the frame of the Hubbard model. And just want to remind you that this model exhibits a quantum phase transition. So you have 2 energy scales, hopping and interactions that basically have different effects. So while hopping wants to delocalize the particles, interactions want to localize them. Why? Because when the interaction energy U, so repulsive interaction, is much larger than the tunneling, so the atoms want to suppress, so the system wants to suppress particle fluctuations in order to avoid configuration of double occupancy in the same site, that is called a doublon, that is energetically costly. And so in order to do that, if you are at half filling, so 1 particle per site, the system, when U is large enough, changes from a metal to a Mott insulator. There was a question over there? Yes. Yes, Fermi. Yes, this is Fermi-Hubbard. Yeah. So you have the same similar physics also in the case of bosons, but we are dealing with fermions. And a very simple-minded picture of this transition that I will reuse in the following is sketched here. So when the hopping is small, so in the atomic limit, so basically you have the energy depends on the occupation of the particles. So you have here an energy U that corresponds to the energy of a doublon in a site. When the hopping is introduced, when the particles can move, so these discrete energy levels, if you want, becomes Hubbard bands. So these bands are getting bigger and bigger in width as the hopping is increased. And at the point in which the hopping is increased above U, these Hubbard bands mix, and so you recover the metallic limit. So this transition from a metallic state in which you can have particle fluctuations to the insulating state in which particle fluctuations are frozen can be understood very qualitatively on the basis of this picture. And I will reuse that in a few minutes. So this is why I wanted to show you this now. Okay, so this is the standard Fermi-Hubbard model, but there is one can do and one can study more complicated versions of this model. For example, SUN Fermi-Hubbard models. So what do we mean by SUN Fermi-Hubbard models? We mean models in which fermions can have more than these fermions can have more than 2 internal states. So this corresponds to spins which are larger than 1/2. And these can be realized in the experiment because remember, our fermionic atoms have spin that is larger than 1/2, it is 5/2. So we have in principle many spin states which are available. So we can realize Fermi-Hubbard models with more than 2 states. And in particular, so as I will show you in the next slide, so the repulsion between the particles will be the same regardless of a spin state. And so these kind of SUN Fermi-Hubbard models have been studied quite a lot, also because, from the theoretical point of view, also because it is expected that at low temperature, so in the Mott insulating limit, one can have different forms of magnetic ordering. So in the case of a standard Fermi-Hubbard model, the ground state is an L antiferromagnet in 2D on the square lattice. While if you have more particles, you can have different kinds of orders, some kind of phases like RVB states or even spin liquids that have been conjectured. So there is quite a lot of physics here that has been studied, a lot of theoretical works. I will not address this physics. Instead, I will address something that is, to some respect, simpler, but not less interesting. That is the following. So now let's focus on what we realized in the experiment. So the simplest extension of a SU2 Fermi-Hubbard model is the SU3 Fermi-Hubbard model, so in which we have fermions that can be found in 3 different states. So we can also label them as red, green, and blue for simplicity. And this system is described by this Hamiltonian. So this is just the Fermi-Hubbard Hamiltonian, where now the spin index can have 3 different states. And this system exhibits a global SU3 symmetry. In which sense? In the sense that if you permute the spins, so if you apply any spin permutation on the system, you end up with the same Hamiltonian. And why it is like that? Because the tunneling is the same whatever is the spin state. So the red particles tunnel with the same amplitude as the green particles, as the blue particles. In addition, interactions are also the same because of properties of our atoms. So if you have a site with green and red, so you have the same interaction energy cost than a site with green and blue, or a site with blue and red. So again, this U does not depend on the spin state. So this is the origin for this global SU3 symmetry. So you can perform any transformation in the spin sector and you end up with the same system. So it is interesting now to consider, yes, please. Okay, so I now I'm not prepared to answer to this question. So
I guess you takes T1, like if you're putting on the red, green, and blue, it takes C red to minus C red, but keep the others the same.
I don't know. If it's fine, let's discuss it later. So, yeah.
S equal to 1 SU2 representation should make an SU3. So it means something it's not needed from algebra.
Okay.
Some extra property to create the other generators that belong to SU3 or do not belong to SU2.
Okay, so I had some slides here that I trashed, but yeah, but okay, but I mean, you all know much better than me. I'm a poor experimentalist, but I can tell you that it is well accepted that this kind of system has this symmetry. So, but yes, I will be happy to discuss that with you later. Okay. So, but the point now is we are interested in seeing what happens when you break this symmetry. So in the form of an additional term that we can put explicitly. And this symmetry breaking term that we add explicitly is a coherent drive between two of these three states. So with lasers, we can induce a coherent coupling between blue and green that is here explicited. So it is a term like omega, that is the Rabi frequency for this kind of process, times C1, 1, 2, 3 are the spin states, C1 dagger, C2 plus the conjugate, Hermitian conjugate that is not written explicitly here. So this is a term that breaks the symmetry, so it acts only on two of the three spin states. So you might wonder, you might realize that these will have some effect, of course, and already at a single particle level. So this will lift the degeneracy between the three states. So red, green, and blue will not have the same energy anymore because of this coupling. In particular, the coupling is between blue and green, and so you will create two dressed states, the symmetric and anti-symmetric combination that will have different energy. So already at a single particle level, you will lift this degeneracy by an amount that depends on the strength of a coupling. So now we are interested in observing the many-body properties of a system. And so we perform a very simple measurement that is what has been performed in the first experiments working with Fermi-Hubbard systems with cold atoms. This is a measurement of double occupations. So we can basically count the number of doublons that we have in the system with a quite simple experimental measurement. So we shine a laser, and this laser can excite only the sites in which you have two atoms. So these two atoms can form a molecule, so you can photoassociate a molecule formed by these two atoms. These molecules are then decay very rapidly, and from the losses of atoms in the system, we can extract the number of particles that were in doubly occupied sites. So we can count the number of doublons, and the number of doublons is associated to the many-body state, in the sense that if we have, and this is exemplified in this typical experimental measurement. So what we do is the following. So we count basically the number of doublons as a function of a total atom number. And so you see here two different data sets. So data set A and data set B. So what is the difference? Data set A, the number of doublons increases basically continuously with a total atom number. Data set B, instead, you have almost zero doublons up to some point, and then the number of doublons increases. So these two data sets correspond to two different many-body quantum state, so that are here pictured in this animation on the left. So this is what you expect to happen. This is a very naive representation. In the non-interacting case, when you have a metal, and so you put more and more particles in the system, and so the occupation increases, and so you have, finite probability of having doublons in basically for whatever particle number, starting even from very small atom number. Instead, if you have a Mott insulating state as this, in which the particle fluctuations are suppressed. So if you increase the atom number, so basically the system increases in size, but you don't have the formation of doublons. So this system is incompressible, and you can measure that by observing this plateau in which you put more and more particles and you do not form doublons in the system. And so this, as I said, this corresponds to the two regimes of an SU3 metal for dataset A and an SU3 Mott insulator for dataset B. And so, what do you see here? So here in color scale, you see the average number of doublons, so this doublon fraction, as a function of the interaction, so the repulsion between the particles U, and this coupling omega that we induced between the two states. Okay, and let me guide you through this plot. So first, if we take here a cross section along the horizontal line, so omega 0, so the SU3 Fermi-Hubbard model. So we increase the interaction, so we observe the number of doublons going down. That is fine. So this is, again, what you expect for the Mott localization process, in which repulsive interaction suppresses particle fluctuations, and so you enter the Mott insulating state. But you also see that you have a similar behavior now when you consider a cross-section along the vertical line. So if we sit here at some value, finite value of interaction, and we increase the coupling omega, again, we see that the number of doublons is going down. So we observe that this symmetry breaking term cooperates with interactions, with repulsion between the particles, so favors Mott localization. So we have this scenario in which the two processes help each other in localizing the system. So let's try to give some explanation, simple explanation for that. And now I will reuse this I was showing to you before. So this is the same figure as before, where we have hopping, and this is the Mott localization process. So here for 3 states, so you have 3 different Hubbard subbands. So if you increase hopping, again, when T is large, these Hubbard subbands will mix, and so you have the transition from a Mott insulator to a metal. But something similar you can have also in the presence of a coupling, because I already told you that at the single particle level, this coupling will lift the degeneracy between the states. That will not have the same energy anymore. Now we'll have 3 different energies. And if now you introduce tunneling, you expect something similar to happen. So you expect tunneling these discrete energy levels to become bands. And so when these bands will overlap, again, you will have a transition from an insulating state that in the non-interacting case is a band insulator, not a Mott insulator, to a metallic state when the hopping is large enough. So the scenario is similar. Now, in the experiment, we have both interaction and omega and the coupling. So this scenario that is very simple here, simply plotted in the 2 limiting cases of 0 interaction and zero coupling. So these 2 scenarios are mixed together. So the situation is the system is richer and more difficult to study. At least to describe it in simple terms. So one requires either a quantum simulation or a lengthy and costly numerical simulation, but this is the physical intuition in these 2 extreme limits.
Yeah.
Yes.
Along the vertical line, you're increasing omega, right?
Yeah. Exactly. Yeah.
There's the other guy. You're plotting functional hopping. Functional.
Yeah. Yeah, right. So what I did not tell you, sorry, is what do we have? So here, I did not tell you the meaning of this D. So this D is basically the tunneling. So it's the single particle bandwidth. So is 60, where 6 is the coordination number of the lattice. So this D is basically the tunneling apart from a numerical prefactor. And so yeah, that's it, yes. Yeah. Yeah. So mostly it is the tunneling, not because we are changing, when we move along this horizontal line, we are changing the depth of the optical lattice. So mostly we are changing tunneling. We are also affecting a little bit in the U, but mostly we are changing the tunneling. Yeah, exactly. Yeah. Here is 3-dimensional. Yes. Yes, I did not tell you, this is 3-dimensional. But this kind of physics is, from what I understood, is kind of general. So it does not, it's not peculiar of the 3D system, so you can have it also in different dimensions. Yeah, and also to convince you of that, so we have compared our experimental results with different theoretical approaches, numerical theoretical approaches. One is one-dimensional DMRG. So, and in 1D DMRG, you observe basically, okay, the numbers are not the same, but because of many different, one is 1D system, one is a 3D system, then you have, this is zero temperature DMRG, but you can see that the plot behaves quite similarly to the experimental plot. So again, U and omega cooperate in localizing the system. And also we can compare with, these are numerical calculations performed in a group of Massimo Capone with DMFT, that is, works better in higher dimensions. And there you see that the number of doublons decreases as you increase the omega, as we observe in the experimental plot. There is some deviation because, again, because this is zero temperature calculation, while we have a finite temperature in the experiment that we believe is the reason for the mismatch, quantitative mismatch between theory and numerical calculation. And so how I'm doing with the time? Okay. And very briefly, so I would like to tell you, yes, please. Yeah, so our the temperature is on the order of a tunneling, of a hopping. So temperature is on the order of a hopping, and when we are in the Mott insulating state, so is much lower than U, and so we are in a regime in which we can observe the Mott physics, at least in the charge sector. So we are cold in the charge sector, we are not cold in the spin sector. But this is mostly, I mean, so the temperature is not smaller than the super exchange energy in the system. But we can observe this physics that is mostly physics in the charge sector. So we were driven to this kind of system by discussions with a group of Massimo Capone that is works with these exotic materials, iron-based superconductors, and I don't know basically anything of these materials except for the fact that these are complex materials in which that cannot be described in terms of the simple Fermi-Hubbard model. This is because these iron-based superconductors are based on the conduction properties of the electrons of the iron atoms that naturally occupy many orbitals. And so as a consequence, one has to write some complex multi-orbital Hubbard model that is much more complicated than what we have in the experiment, because here you have multiple degrees of freedom. So you have a spin degree of freedom, you have an orbital degree of freedom, so more complicated Hamiltonian, but at the end you have something similar. You have a multi-component quantum system. You have just 3 components in ours. And you have these coherent couplings that in this are given by Hund's coupling, magnetic coupling between the orbitals. So these materials are kind of complicated beasts, but you have as you can see in this phase diagram taken from this paper, something in common. So in this phase diagram, you have repulsion, again on the horizontal axis. You have the Hund's coupling, so the coherent coupling between orbitals in the vertical axis, and you see something similar to what you see. So the coupling between orbitals will shrink the metallic phase, so will enhance the localization. So the localization point is shifted towards lower values of U. That is reminiscent of what we see here. And also it is predicted that you can have new quantum phases like this orbitally selective Mott phase, in which some of the particles, of the states will localize, others will not. So you have a state in which the conduction properties are different according to the spin state you're considering, to the orbital you're considering. So we tried to observe things like this, so these state selective properties, that in some sense are also natural to emerge when you break the symmetry between the orbitals, between the states. We have a simple measurement, so it's a variation of a measurement that I showed you before. So in which now we can count separately the number of doublons in each channel. So this means that we can count the number of doublons made by one blue and green particle, by one green or red particle, or by one red and one blue particle. So we can count this number of doublons independently by changing the frequency of a laser that performs this photo association. And so this is the last slide of the first part of my talk. And what you see here is this quantity here, this experimental measurement of this quantity that is the fraction of doublons in one specific channel, that is the blue-green channel. Now, and I remind you that blue-green are the two states which are coupled by the external coupling. And so here what we see that when the coupling is 0, we get 1/3. Okay, that's fine, SU3 symmetry, and so we have 1/3. So equal number of doublons for the three states. But then when omega increased, you see that the number of doublons in this channel go to 0. So I don't have the number of doublons in the other two channels here in this slide, but this stays at a finite value. And so why is it is like that? Again, one can give some simple explanation in terms of the single particle mechanism that I was showing to you before. So in order to form a doublon in the blue-red channel or red-green channel, you can just occupy the two lowest states, red and this symmetric combination plus, that is blue plus green. Instead, in order to have doublons in this blue-green channel, the only possibility, so these are fermionic particles, so is that you have a plus and a minus state in the same site. And this has an extra energy cost because you have to pay this extra energy. So energetically, this is more costly. And so this is why this, the very simple explanation, while these doublons will acquire this state selective character. So we observe some state selective particle correlation in the system that are driven by these mechanisms. So in some sense, one can also say that if you can form doublons more likely in these two channels than in this channel up here, so this means that red particles will have some higher mobility, so can tunnel more conveniently through the lattice rather than the blue-green particles that instead do not want to sit on the same site. So these are just some first results. So in the future, we'll perform more experiments in order to characterize the properties of this system. And just to summarize this first part, so we have realized this multi-component Fermi-Hubbard system with this controlled breaking of this interaction symmetry, observing enhancement of Mott localization and the evidence of flavor selective correlations that is in agreement with what is studied in the context of these multi-orbital Hubbard models that have been introduced to describe these strongly correlated materials. And yeah, perspective, so kind of further characterization of dynamic characterization of these SUM broken states, also probably some transport measurements. And also, and this connects to the second part of my talk, it would be interesting to also study what happens when this coupling between states is not just in the internal space, but it gives rise to some form of spin orbit coupling. So when we could apply some momentum kick to the particles when we flip the spin, and so this has some possible implications for the generation of topological interacting states. Okay, so okay, roughly half of my time. So if you don't have questions on this first part, I will move to the second one. Yes, please. Okay, particles in the system. So in the whole system, we have something like 10 to the 4 particles, 10 to the 4. So the filling is on the order of 1 particle per site.
Because we have a lot of particles that have no creation, because a priori in the measurement, you are still have because you measure the number of protons, the mechanics is to find some is
Yeah. So, but we, yeah, but we always perform some ensemble measurements. So we measure all the particles at the same time. Does this answer? No. We average over several measurements, yes.
It doesn't mean.
Yeah, that is just me, yes, sure. But yes, so but also in the single shot, we measure all of the sites together. Yeah, it's already some, yes, it's already some ensemble mean, and then we average over different experiments, yeah. Yeah. So there are many. So one explanation for that is, of course, temperature. So we have some thermal fluctuations in the system, but then another reason is that we do not have. I mean, I was simplifying some aspects of experiment. For example, the fact that we are not dealing with a uniform system, so we have a confining potential, and so this confining potential will smooth the transition. Will contribute to the smoothing of the transition. Yeah. Okay, I don't have. I mean, let me try and. Okay, if we can make it after the talk, maybe I can recover also some other slides that I'm not. Okay, but I will stay here after the talk, and so we can discuss it later. Okay. Okay, second part. Second part is very recent results that we got in the experiment, and you can find them in this paper that will be published soon in Science. So here we have studied the Hall effect in the system of these fermions in lattices. So this work was performed in collaboration with a group of Thierry Giamarchi and Michele Filippone. Thierry Giamarchi in Geneva and Michele Filippone in Grenoble. So before that, I need to introduce one tool that we have developed in the last few years that we called the tool of synthetic dimension. So that is something that might seem exotic, but is instead something very simple conceptually. So we have these spin states that now, as I also showed you before, we can couple with some lasers, so we can induce these coherent spin flips by just shining lasers. And now, if we think to this situation, so spin states with this coherent coupling between quotation marks next neighboring spin states. So what you see here is pretty similar to what you have in a lattice, when you have particles sitting in discrete sites, and then you have a coherent coupling, that's a tunnel coupling, between next neighbors. So basically the idea here is to treat the dynamics in this internal space as if it was a dynamics along a fictitious dimension that is not x, y, and z, but is a dimension that is encoded in the internal degree of freedom. At a single particle level, the Hamiltonian is the same. So you have the same type binding Hamiltonian where now the Rabi frequency of this coupling plays the same role of a tunneling between one side to the next neighbor. Okay, so this is an idea that was it's already 10 years old. So it was contained in this paper by the group of Maciek Levenstein. And at the beginning, so the idea was really to try to simulate something, a model that is not in 1D, 2D, or 3D, but is in a higher dimension, for example, 4D, where this fourth dimension is encoded in the spin state. So instead, we're using this approach to realize some physical systems of interest, and in particular, this is the configuration that we studied, that we first implemented in this paper in 2015. And what do you see here? So this is a kind of two-dimensional system, or let's say a ladder system, where one direction is real. So this is real space X. So this is what happens in the lab. Then we have these lasers that will induce the spin flips. And these are so this, technically speaking, is a Raman transition that is induced by two lasers. So one laser coming from this direction and one coming from that direction that will induce a spin flip because they have different polarizations. And so this spin flip can be imagined as a tunneling along this fictitious synthetic dimension. But now the interesting part of the story is the fact that this coupling can have a phase, can be complex. It was not complex in the first part of my talk, it is complex now. This complex, why? Because it is induced by laser beams that will propagate in space. So we'll have a phase factor, that is the propagation of a laser wave. And a very simple calculation shows that Rabi frequency associated to this spin flip matrix element has a phase that depends on position. So at the end, we can write this tunneling in the synthetic dimension has an amplitude omega times e to the I phi j, where j is the site along real space X. And so this phase is a kind of Peierls phase that is imprinted on the atoms. And so the result is the following. If you consider the tunneling of a particle along a unit cell of its structure, the phase that the particle gets on this link is different from the phase that it gets on this link. And so as a consequence, when you perform a closed loop and the particle comes back to the initial position, it will get a non-zero phase, an Aharonov-Bohm phase, that is analog to what happens when you have a charged particle in the presence of a magnetic field. So this is a way. There are many ways to do that in cold atom quantum simulation experiments, and we have some reviews here. But the idea is that you can, with this trick of a synthetic dimension, very easily study the system of particles with a fictitious charge in a magnetic field that can be controlled very conveniently. Okay, and so we performed some first experiments in 2015, so I will be very fast on that. For example, in these first experiments, we studied the emergence of edge currents in the system. So edge currents is what you have for example, in the quantum Hall effect, where you have a bulk that is insulating, and so currents can flow at the border of material with a well-defined direction of circulation that is associated with a direction of magnetic field which breaks time reversal invariance. And so we have studied these currents in this first paper here. And if you have some edge currents moving counterclockwise, like that depicted in this picture, so it is very simple to observe them experimentally, because what you see is particles in this red state, that is the upper edge of this ladder, moving preferentially towards the left. So this is a measurement of a momentum distribution of the particles. So we observe an imbalance of the momentum distribution function towards negative values, while particles in the blue state, that it is the lower edge of this ladder, will move preferentially towards the right, so with positive momentum. So this is a very simple and direct observation of this chiral motion in this synthetic dimension picture. And so, and there we also studied, for example, the behavior of these chiral currents as a function of a magnetic field. And there are some interesting observations are reported here. And just very briefly, and then I will move to the, okay, but maybe I can skip that. Very briefly. So what you see here, when you increase the flux, so the magnetic field, so these chiral currents at some point will change direction. So J is a measurement of this current, so positive values means clockwise, negative values means counterclockwise. And so why does this happen? So for a moment, let's think in classical terms. So in classical terms, what should we expect? We should expect the following. So if we don't have any magnetic field, no chiral current, so no breaking of time reversal invariance. Fine. If you apply some magnetic field, we know that classically particles will perform some cyclotron motion. So with a direction that is set by the, classically speaking, by the right-hand rule. And it makes sense that these chiral currents can be thought as the kind of macroscopic manifestation of many microscopic cyclotron orbits. And if you increase the magnetic field, it's natural that these chiral currents should increase. But then at some point they go down. Classically speaking, it does not make sense. So you increase the magnetic field, so the cyclotron motion will decrease. But what it makes even less sense is the reversal that you have when you keep increasing the magnetic field. So classically speaking, it is a right-hand rule that becomes a left-hand rule. And why is it like that? It is like that because of, now we should remind that the system, of course, is a quantum system. And importantly, this system is not defined in the continuum. It is defined on a lattice. And if we consider the value of a flux for which this reversal of a current happens, so this value corresponds to half of a quantum flux through the unit cell, so a phase of pi. So this would correspond to a very strong field of 10 to the 4 Tesla if we translate the effect into what you should, a magnetic field that you should put in a real material. So these are very strong magnetic fields. And so what happens at this point, so is the following. Now we can just remind that that the magnetic field is a phase in quantum mechanically speaking. And so the current for a flux phi should be equal to the current for a flux phi plus 2 pi. So when you add a quantum of flux to the system, you should observe the same behavior because quantum mechanically speaking, the magnetic field is a phase. So this is one of the symmetries of the problem. The other is the time reversal symmetry that tells you that if you reverse the magnetic field, you should reverse the current. So if you combine these two symmetries together, you realize that this function should vanish at a flux equal to pi, and then it should change sign. So this is very simple consequence of these two symmetries. But for those of you who are more into topological quantum physics, this is also connected to the behavior of a system in a full 2D limit, where what we realize is basically the Harper-Hofstadter Hamiltonian, so tight binding lattice model, square lattice with a magnetic field that is pictured here, and this is the spectrum that is the famous Hofstadter butterfly. But if you consider the topological invariant associated with these states, that is the Chern number. So the Chern number changes sign when you cross the point of pi flux. And because of bulk to boundary correspondence principle, when basically the Chern number is associated of a bulk is associated with the properties of edge states. Also, when the Chern number changes sign, the direction of the edge states will invert. So this is not a 2D system, so we study just ladder system with very few sites, but I mean, what we observe can be connected with the physics, with the concept of topological quantum physics here. So now, last 10 minutes, I will show you the recent stuff. Yes, please.
How is this current response parallel? Because for ordinary quantum effects, the spin that has been downstage that propagates but your spin is kind of taken as something to form your lattice.
Yeah. Yeah. So here you should think, I mean, if you accept this idea of synthetic dimension, you should now just forget of a spin. So this would be just a spinless particle. So you use the spin to encode the information on the. Why? So yeah. So chiral in the sense, I mean, not in the sense of a spinel effect. So in the sense like what is pictured here. So, I mean, so whatever is the spin up or spin down will circulate in the same direction. Okay.
That picture is for the quantum spinel effect. But you don't speak of the spinel effect.
No, for the quantum Hall effect, it's not spin. So they're going in the same direction because you have the magnetic field. Yeah. Okay. So last 10 minutes. So is the new results. So we have performed. We've used this system to measure the whole response in the system. So really go to some very simple experiment. So the classical experiment in which you take material. So you let a current flow in the material and you observe how. So this is a classical picture of the Hall effect. So you have the current, and so the Lorentz force that bends the trajectories of a particle. So you have the accumulation of carriers on one side with respect to the other. You have the counter field, the electric field that builds up in the system, and you develop a transverse voltage drop. And so you can measure, characterize the system by measuring the whole resistance. And I mean, this is something that is very well known and well understood for non-interacting systems, for non-interacting electron gas. I mean, okay, of course, the Hall effect is important for a billion of things, from the classical limit for building devices, magnetometers, or characterizing materials and so on. And of course, you have a quantization when you go to large fields. And you also know that in the presence of interactions between the particles, the situation changes. And so in the quantum limit, so you can have fractionalization, and so you can have the fractional quantum Hall effect. But even in the small field, you can have deviations from what you expect from a non-interacting Fermi gas pictures or Fermi liquid picture when it comes to some strongly correlated materials like, again, ITC superconductors or low-dimensional systems. And driven by this theoretical proposal by the group of Thierry Giammarchi, we decided to try to study the whole response as a function of interaction between the particles. And so this is what we did. So basically, the system is similar to what I showed you before. So again, with this trick of a synthetic dimension. But now we apply a current. So we apply a current, we drive a current in the system by applying the analog of a voltage along the real direction. So we induce a current, and then we observe how this longitudinal current will develop a transverse voltage. Transverse voltage, between quotation marks, that we can measure by basically measuring the imbalance in density on the two legs of this ladder. So what do we do? So we apply this current, we measure this current by performing some ordinary time of flight measurements. So we measure the momentum of the particles and then the current. And then we measure the imbalance of population on the two legs with some very simple measurement. Okay, and then we measure this quantity here. This quantity is a proxy of a Hall resistance. So it is not a Hall resistance because also in our system we do not have. So the idea of a resistance is not ill-defined because in some sense we do not have equilibrium, so we have ballistic transport. But we can measure this quantity that is related to the Hall resistance because it is basically this population imbalance on the two legs, which is connected to the idea of a Hall voltage divided by the longitudinal current. Okay, and this is what the kind of things that we measure. So as a function of time, we measure the current. So this current is not a steady current. This is because we perform a quench. So we suddenly activate this gradient in the longitudinal direction. So in the absence of magnetic field, the system will perform block oscillations that here are a bit distorted by the presence of a magnetic field. So, but the idea is that you have this time-dependent current. With this time-dependent current, we measure also time-dependent polarization in the system. So we observe this imbalance in population that builds up during the evolution of the system. And if you divide these two quantities to measure this Hall imbalance, you observe that the ratio of the two converges towards some limiting value quite rapidly. So on the order of a few tunneling times, so within experimental errors, and so the curve that you see below is the theoretical prediction. So you get to some kind of steady value. So even if this is a kind of non-equilibrium dynamics, so at each time, so even if these two quantities will change in time, the ratio is well defined. And then these some predictions, theoretical prediction. Okay, so what we studied is how this steady state Hall imbalance depend on the system parameters. So here, we first studied how it depends on the tunnelings, for example. So this is the Hall response as a function of Ty over Tx, so the tunneling, the synthetic dimension divided by the tunneling on the real direction. And you see that this depends on this quantity, but at when Ty over Tx is large enough, this approaches a limiting value. So we have also additional points that I forgot to put on this slide. So we have also some points here, and really this arrives to a steady state value. That can be understood in terms of this picture that you see here, that is basically the spectrum of a system as a function of, for different values of Ty over Tx. So, and basically when the transverse hopping is large enough, basically you have two bands in the system that will separate. So you will have a gap that opens between the two subbands. And so when this happens, so basically the response of a system does not depend anymore on the details of a system, so in particular on the value of Ty. So you have this kind of universal response that can be derived from the theory by the group of Thierry Jamarchi, and has this analytical value. And also, and this is the more interesting part of the story, you can measure how this depends on interaction. So we can change the repulsion between the particles. That, by the way, so it's kind of a strange repulsion here, because this repulsion is between particles sitting on the same rung, not on the same site. So the interaction is between a particle here and the particle here. And again, we can observe this behavior, in which, as a function of u, and this my last slide, so the response of a system changes. So this all imbalance changes from what you expect from the non-interacting theory to what you expect when this universal value that happens, that sets in when the repulsion between the particles is very strong. So we clearly see an effect of atom-atom interactions on the whole dynamics of the system. And in particular, so we recover these limiting universal value. This is predicted by theory at large interaction strength. Okay, and so this is, so I think I can conclude here. So, okay, I think my time has end up. So just outlook of the second part. So we have performed these experiments in which we have measured the build-up of a whole response after sudden activation of a current in the system. And so we have studied for the first time the effect of interactions between the particles in a regime, in a quantum simulation of the whole effect. So identifying this universal regime, and there are some perspectives, and one of them, and just in one slide I can tell you what we're working on at the moment, is the measurement of something that is more related to the whole voltage, really. And a way to do that we're working on at the moment is the following. So we can perform the same experiment as before. But now we can also add, similarly to experiments which are performed in solid state physics, we can add an additional gradient. So we can add an additional electric field, if you want, longitude perpendicularly, so in the transverse direction. And we can find the delta Vy that cancels the whole response. And these are some preliminary measurements for that. So what you see here is the polarization as a function of this transverse voltage. And so at zero transverse voltage, you have some polarization because of a whole drift. But then at some particular specific value of a detuning, so sorry, I didn't explain how we do that, but so you can read here just delta Vy, so this is delta Vy. So some specific value of delta Vy, we have a zero whole drift. So, and this is basically the whole voltage for which we cancel the whole response. And so these are first measurements, and we want to measure how this depends on the system parameters, eventually trying to observe some nice behaviors function of interaction and other properties like feeling of a system and so on. Okay, this is the conclusion. So these are the people who work in the experiment. So Tianwei Zhu, Jacopo Paravicini, Giacomo Cappellini, Massimo Inguscio is a long-term collaborator, and Jacopo Catani and other younger team members. For those of you who are interested, but I will not tell anything about that because of time, we are also building new experimental setups. In particular, we are building a system with programmable arrays of atoms, individual atoms, with Rydberg excitation. So we have a setup that is under construction and will be working at the end of the year. So if you are into Rydberg physics, so if you have interesting ideas of experiments to be performed on this platform, so we can discuss it, and I will be very happy of telling more to you. Okay, thank you. Yeah, there are some ideas to do that. We have not tried, but yes, there are proposals to do that, but we have not tried yet. We should. The smallest flux, okay. I think there is no. So okay. So good question. So. So the flux will depend essentially on the angle of your beams. So forgive me for the okay. Okay, it's a bit late. Okay, so it basically depends on the angle of these excitation beams with respect to the lattice. So I mean, it should a small magnetic field should mean a very small angle. We can put numbers and to try to understand. I mean, I would say that something like a magnetic flux of 1/10 of a quantum of flux is easy. 100 is a bit less easy because it will. I mean, we've not tried actually to do that. It would imply a very small angle that in principle can be done, but then at some point it will become very. You will be very sensible to the angle. So I mean.
How well resolved, supposing you're trying to study the Hofstadter spectrum.
Yep.
How well resolved get the different lobes to.
Yeah. So what is the question specifically? So. The energy resolution. Yeah. So the energy resolution. So we have. So, I mean, of course, if you want to study this, you should figure out some spectroscopy probe. Should do some spectroscopy on the system. And we had some ideas for that. And that works nicely with terbium atoms, because the terbium atoms are those atoms that you use also for building optical clocks. You also use a strontium or this class of atoms, 2 electron atoms, and you use them for building optical clocks because they have some very narrow laser transitions. So you can perform spectroscopy on these atoms with 1 Hertz of resolution, and this spectrum will have some bandwidth on the order of typically a few kilohertz, or tens of kilohertz. So one could have a resolution of 1000 on the energy axis. And of course, yes.
Sorry, coming back to your first experiment, you
Yeah.
have order 10 to the 4 particles,
Yes.
10 to the 4 sides,
More.
3 dimensions.
Yes.
Okay.
Right.
Only one more question.
So, if you're using with the medium, you said the thing has like 5.
Wait a moment. Okay. Can you please repeat?
5 in space.
Yes.
Why is the dimension in the on your experiment the specific dimension only the 3 sides?
Because we are lazy. No, and I can answer. So this is a kind of very technical thing. So posso usare un po' di lavagna? Okay. So this is a very technical thing on this. So when you, okay, you have these, in principle, 6-spin states. Then when you apply the coupling, so what happens is the following, because of atomic physics details. You do not only couple one state with the next one, but you also apply some energy shift, some light shift. So that causes the states to have different energy. So this is why if you don't take care, I mean, you just couple efficiently only two of the states. And this is, for instance, why if we do not compensate, if you do not play any trick, we just couple two of them. Because these energy splittings will be different from each couple of sites, and so you can couple efficiently only these two, if you start with just atoms in this p state. Then in order to make three, we played some some tricks, but I mean, coupling all the six of them with Raman processes in which each of these coupling is a couple of lasers, in which one photon is absorbed and the other is re-emitted, keeping the directionality of a process. So you want to always to absorb a photon from a specific laser beam and then remit a photon in the other mode. In the other laser beam is not so trivial. So I mean, there are some complications that we need to take care of.
But you could, I mean, overcome this problem in the future, or is it really impossible?
No, it's not impossible. So no, of course, this is interesting, and this is really interesting because I mean, in these experiments, so these are really ladder systems in which, I mean, the notion of edges and the bulk is not so well defined, of course. Going towards 16 states is already something that will, for instance, there are some experiments, recent experiments performed in Paris at LKB with different atoms, with different technology, in which they were able to couple something, maybe even more than 10 sites. And there you observe some different physics happening at the edges from what happens in the bulk. So that goes in the direction of possibly studying the quantized Hall effect and other interesting things.
Is there like do you have an idea of the correlation length in this?
Yeah, correlation length. I think I made some calculation in the some time ago, and I do not remember it. Oh, it depends on the parameters. So, but it is on the order of one or two sites, maybe two sites. I feel on the order of two sites. Yeah. Yeah.
In the first experiment, when you have this terminal braid symmetry, how do you implement it with lasers?
Yeah. So we implement in the same way. So is but so the difference is that that coupling was not a complex value coupling, so it was a real valued, and the real valued coupling is I mean just obtained when these two beams have the same direction. So if these two Raman beams have the same direction, you do not have any phase, basically. So the phase is that you could have a phase, but this phase is not dependent on position because it is the same for every value of x. And yeah, so it's again a Raman process, but you don't have any phase dependence, any position dependent phase.
Have you tried the 40
No, we have not tried. So this is interesting. So for the Hall effect, so something related to the 4D Hall effect has been studied in in other experiments at MPQ by working on a different idea. So on the idea that, I mean, not really on the Harper-Hofstadter model. So working instead with Aubry-André models. Aubry-André model is is a model that we also studied in the past. Is a tight binding lattice model where you put some sinusoidal incommensurate modulation below the main lattice. So this is a 1D lattice that, because you have these two length scales, one is the length scale that is associated with lattice spacing, and one is the length scale that is associated to the modulation of the energies. To many respects, so I exhibit some properties that are similar to what you have in the Hyperhofstadter model. And so with a combination of two quasi-periodic lattices, one in the x direction, one in the y direction, you can simulate some physics that is connected with the Hall effect in four dimensions.
I asked about this
Yeah.
dimensions because I struggle to understand. So it's like, so you have so the strength of the coupling depends on this, say, whatever quantum number, let's say spin, right?
Yeah.
And then you say, oh, so that's like another dimension. But
Yeah.
But then it's like, I don't understand in what sense is that another dimension, because it's like if you have, for example, long range interaction, like let's say that each atom, whatever particle interacts with like 10 another particles, then it would be like 10-dimensional. Like, I don't understand in what sense do you mean like synthetic dimensions? In what sense is that a dimension?
No, I mean it in this sense. I mean, so don't think to interactions for the moment. So let's think to the non-interacting particles. So if you apply this, if you play with this trick, a particle can move in the real direction, so tunnel in the real direction from one real site to the next neighbor, but can also perform this spin flip driven by the laser. And so when you have a spin flip, you think to this spin flip as if it were a hopping process along this fictitious dimension.
Right, you think about it like this, but then it's really not, right? So
Yeah, of course, yes. Okay, yeah. So we live in 3 dimensions.
but like whatever kind of other quantum number, you can always play this game. You can always.
But yes, but this is quantum simulation. So all the business of quantum simulation that we can, I mean, we can say that this is useless, fine, but all of this business is based on the implementation of some Hamiltonian onto some physical system that is different from the system that it was initially considered for that Hamiltonian, in some sense, if you want. When we have an optical lattice and we pretend to study we pretend that the atoms in the optical lattice will behave like the electrons in a solid. So we are basically forcing the atoms to behave according to the Hamiltonian that describes the electrons in a solid. And here we are doing something similar. So we implement this Hamiltonian in the spin sector. That is the same Hamiltonian that describes the dynamics of particles in a lattice. And we pretend that this spin dynamics is a simulation of that physics.
Definitely. Because you're using atoms with a more complicated structure than
Yeah.
usually taken. Can you also exploit that fact by creating more than one synthetic dimension? By using more than one extra?
Good question. In principle, yes, and actually we also did it, but not simultaneously, because in different experiments we both. Sorry for the seasick. Okay. In different experiments, we both applied this idea to the nuclear spin states, but as I told you, you have also this possibility of exciting the electronic degree of freedom. So because of these terbium atoms have these metastable excited states, And we also implemented that with an optical transition between the electronic states. And actually, some of the results that I show you were obtained also with this approach. We did not combine them together. That could be interesting. But this would require some extra work to implement Raman transition in the upper manifold, but it is some interesting thing to be considered. Yeah. Yeah. What kind of problem? Sorry.
Well, finite size problem in some sense.
Yeah.
What you have finite in many side in one direction.
Yeah. So we are. Yes, this is definitely correct. So we are. I mean, the physics is really dominated by finite size effects, of course. But some of them, I mean, depending on what you would like to observe, for example, the whole response can be observed.
It's not really the dimensional thing is really reduced. So universe is the phase diagram of cubes really useful in that sense.
But you meant for the first but in first part I did not invoke this synthetic dimension. So these were really a 3D system. So there, if you want, I use the spin degree of freedom. Yeah, just yeah. Yeah. It's not. That's not huge. Oh yes. Yeah. Right.
Other versions? It's also interesting to apply synthetic dimension in periodic boundary conditions.
Yeah, definitely it is. And we had tried, and I'd say that we were working on that just before COVID arrived, and then we put the project on the side, and we should resume it. Yeah, by the way, it has been demonstrated in some experiments. So in an experiment by a group in, I don't remember if it was in Hong Kong or in Seoul, it was demonstrated that. That, of course, is, I mean, is interesting. And, okay, I don't have the slide to, okay. One could do it, but by playing some tricks. So, yeah. Or using a set of lasers to address different transition between different states, but one can, in principle, can do it.
Other version? Last.
How well do you put the coupling into the system because you made them complex? Is it possible to make them real and intelligent space in order to measure, for example, those so-called full effects or something like this in synthetic model?
Okay, so you said it's possible to make the coupling real or complex? Yes, it is. So and yeah, it depends on the angle of the laser beams. So if the laser beams are collinear, so the phase is 0, and so the coupling is real.
Control the coupling sense that I mean you always have the same coupling, but the coupling depends on space.
The amplitude of the coupling. One could, I mean, if one has some want to implement some form of coupling, in principle it's possible. Then one should look at what specific form of, but in principle, yes. I mean, the amplitude of the coupling is basically the laser power. And the laser power depends on how much light and so on, and the shape of a beam. The phase depends on the direction. It would be difficult to make something that is not a linear dependence of a phase. But a phase gradient, yes, it is simple.
Thank you very much.
Thank you.